So we want to think outside the box today, and I'll explain what I mean by that as we go through this presentation. So just quickly, in terms of agenda, I'm going to give everyone a brief introduction to Bennu Networks. We'll then talk about some of the market drivers in the broadband market and some of the resulting architecture implications of that, and how you can build a network scale to 100 terabits in essentially a single system. And then also unlocking the value beyond just performance, because it's not just about performance as we move forward into this complex broadband market. So just briefly about Bennu, we were established back in 2010, and while we sell globally, we're headquartered in Boston in the United States. We're an industry leader in software-defined edge solutions, so we focus almost exclusively at carrier solutions for their edge of their networks. And we are a heavily engineering-led organization, and this enables us to really stay at the cutting edge of the standards and innovating with new technologies for our customers. We actually have a sampling here shown of our customer base. And as you can see, there's a mix of tier ones to tier twos, tier threes, and we have very large deployments that have been basically running for the last decade. We have about 7 petabytes a day of traffic going through our platforms, which is more traffic than all the wireless traffic in North America. So it's a significant amount of volume, and about 25 million connected homes and businesses. And we work with a lot of great partners in terms of our go-to-market approach. We have also a variety of products, and we're going to be talking primarily about our Broadband Network Gateway, or BNG platform, that runs on our SD Edge platform. And we're going to be talking about how the BNG can evolve into a more flexible type of architecture than what has been in the past. And other products, though, that we support, just so you're aware, is our CGNAT gateway, our Wi-Fi access gateway, and trusted Wi-Fi access gateway, or TWAG. We also support SASE gateway, which is for secure access service edge, to provide security to enterprise or small business customers, and potentially could even be leveraged for security for residential subscriptions. And then we are we're developing a new product, which is the 5G access gateway function in UPF. So that's just a quick overview of some of the products we have in our portfolio. So let's talk a little bit about market drivers and what's going on in the broadband market. So, if you think back 10 years, a lot has changed, and there's some fairly significant technologies that have almost essentially been invented or come to fruition. And they have also not only sort of started, but grown to be quite large markets. And I guess, sort of the end conclusion of this is just that the world seems to be becoming, less and less predictable. There's so much innovation occurring. It's really hard to know what's going to happen over the next 10 years. And of course, the challenge with that is if you're working in a service provider environment, you're deploying infrastructure that is sort of intended to last at least 10 years. And so how do you anticipate all these things that are going to occur and grow into massive markets? And as a result, of course, put a tremendous amount of new demand on the network. And so if you look at today, we have 5G evolving and also potentially converging with the wireline market. We have secure access service edge, like I mentioned before, for security services. And this is actually a massive opportunity for service providers because it moves the security function from the enterprise premise to the network. And as a network provider, then the telecom provider can enable this SASE service for the enterprise. It's driven actually even more so by the fact that people are working remotely. And as we've seen, while we thought this was driven just by the pandemic, it's also driven by preferences. It looks like most companies are going to have hybrid work weeks, and there's going to be a lot of people working remotely, which of course extends the enterprise out to the residential home. And that's a completely different paradigm than what we've had in the past. So big opportunities for operators, but also big challenges. And of course, along with this, we've got huge growth in IoT devices. Everything is relying on the cloud these days. Cloud gaming has really increased dramatically. But now we have technologies like virtual reality really coming to market in a much higher volume manner, and augmented reality as well, both driving the need for edge compute because they're going to need low latency. And so there's a big opportunity again for operators to capitalize on that, given that you own the edge of the network and the access networks. And then over the top service adoption is also continuing to grow. And that's driving the need really to push content distribution further out to the edge. So all of these strains on the network are not, these are massive changes in terms of traffic flows, number of devices and number of flows, and the bandwidth that's required. And of course, then finally, the need for edge compute. So how do you handle these market conditions where you have essentially an unpredictable future? You have extremely rapid application innovation occurring and accelerating all the time. The connected device growth is exploding. You have this need for low latency applications that will leverage edge compute. You're faced with increased competition, and you've got to also plan for probably, within the next 5 years or so, convergence of wireless and wireline networks. So how do you manage these risks? Because these are true risks. They're kind of a mix of opportunity and risks. And I think the key is that you have to think about what your access network and transport network architecture is going to look like. And specifically the Broadband Network Gateway kind of being the linchpin of this fixed access network and providing the services to the end customers, whether they're business customers or residential customers, is really the key element that needs to be adaptable to handle this unpredictable future. It needs to be agile so that you can handle new kinds of features and capabilities to support new applications. It needs to be able to scale up in a massive way and also flexibly scale up in multiple dimensions, whether it be bandwidth, number of devices, number of subscribers, so multi-dimensional scaling. There's clearly a need for a distributed edge. That's clearly been, the architecture in 5G is moving towards the edge. The fixed access network is going to need to do the same. And of course, if you're planning for wireless wireline convergence, not only do you need that distributed edge, but you need to be able to evolve to a 5G access gateway function, UPF, and maybe even hybrid access gateway within your BNG node. And the other thing is, of course, if you're facing increased competition, you really need to have a lower total cost of ownership, or TCO, and also be able to flexibly add new service capabilities. So you have some level of differentiation and you're not just competing purely on price. So with all of these new kind of requirements, you really need a new approach. And again, the Broadband Network Gateway is kind of the linchpin of the access network, offering the services to the subscribers. And so the nice thing about technology is it's continuing to evolve. And now we have the opportunity to move from sort of the classic Broadband Network Gateway, which was a chassis-based system really optimized to move bits, to a software-defined Broadband Network Gateway that is really optimized to adapt, to scale in multiple dimensions and to massive levels, and evolve evolve quickly, so with agility. And so you go from an architecturally static and constrained, sort of chassis-based platform to something that's architecturally flexible and open, where you have a lot more degrees of freedom to adapt. So how do we compare these two architectures? So they're actually very similar at the base level, in that you have in a typical chassis, you have control modules and you have line cards. Well, with a software-defined BNG, there's really no chassis in this case. You have control planes, which are essentially the control modules, and you have user planes, which is very similar to your line cards. And the nice thing about this new software-defined architecture is that it is actually the interfaces between that control plane and user plane are standardized, and this has been defined in the CUPS architecture by the Broadband Forum. And it's using some of the same interfaces that are actually used in the mobile networks and 5G networks and similar protocols. And so there's a lot of leverage there. Now, these architectures are quite different. So if you look at your typical chassis from a scaling perspective, it really has a limited number of slots, maybe up to 12, oftentimes less. And each chassis needs to have a control module in addition to the line cards. In the software-defined BNG, you can scale up to 256 user planes. And the user plane size can vary based on the need. Very small user planes for maybe remote locations, very large user planes for more centralized or large metro areas. And the user planes can also be tuned for consumer, enterprise, low latency, et cetera. You could have a variety of different types of user planes. And this can evolve over time. It's not like you are constrained to one deployment that you come out with in the beginning. You can very quickly change things over time. So you have a lot of flexibility there in terms of how you scale your system. Now, there's also a need for scaling control plane separate from user plane, because you may have different levels of growth as the future unfolds, and you may need to have more control plane scaling versus user plane, or vice versa. And historically, we've had to scale these the control plane and the user plane at the same rate, essentially. So there's really no independent scaling, because if you add a chassis, you need to add user planes, line cards, and you also need to add control plane modules. So you have this dilemma that you cannot scale one without the other. And in a software-defined BNG, you have this great flexibility. They're scaled completely independently. And so not only can you add more control plane processing without impacting or changing your user planes, you can do that vice versa. You can add more user planes or distribute more user planes or tune in different user planes, different types of traffic, without having to impact the control plane. And of course, this makes it easier also to add and scale while the network is running in operation, right? You're not impacting both at the same time. Another major difference between these two architectures is if you look at network wide and also the resiliency model. So here I'm showing on the left, maybe 15, 20 systems, maybe 10, 12 slots each. And you've got many different independent systems running here that you have to manage. They oftentimes will have just a one-to-one redundancy. And there's typically either no or limited geo-redundancy. And then, of course, finally, the control plane and user plane have to simultaneously fail over. So if a chassis goes down, you've got to move everything over at the same time, which is, of course, a high-risk, complex failover scenario. In a software-defined BNG, at least in this comparison, in terms of the number of user planes and control planes, this is one system. And because we haven't exceeded 256 user planes. And we can do M-to-N or N-to-1 redundancy. So you get much better economies when you have an N-to-1 or M-to-N redundancy versus 1+1. This also supports geo-redundancy between the control planes and also can be geo-redundant for the user planes if architected correctly. And the control planes and user planes have completely independent failover. So if a user plane fails over, it has zero impact on the control plane. And if the control plane fails over, the user planes can continue to forward traffic while that's occurring. There's no impact on the user plane. So you have better resiliency, a lower cost resiliency, and you have the ability to distribute user planes to the edge in a much more simplified manner, because you're not adding entirely new systems. You're simply adding essentially like a line card. It just is not constrained to an individual chassis. It's now something that you can distribute geographically across your network. And so if you're thinking about scaling your network to support perhaps more rural environments, because there's a lot of government subsidies going for that, it's not like you're adding new systems, you're just adding an additional user plane node. It's much simpler integration, and you can do this, without massive changes to how you're handling your network. So it really does scale. And of course, if you're trying to build a footprint for edge computing, where you can either distribute content distribution, further out to the edge, or you're trying to lay the foundation for the metaverse and have low latency compute available, or you're trying to, enable security level services like SASE for your enterprise customers, within a metro area. This distribution of the user plane really enables all those things, and it's becoming, more and more important. So how do we get to 100 terabit BNG? If you have about 400 gigabits per second per user plane, which is, by the way, a fairly conservative number, since we have servers now that support up to 800 gigabits per second. And you've got a control plane that can manage up to 256 of these user planes. That is 100 terabit network BNG in a single system that is highly resilient and not limited by the kind of physical constraints that you see with a chassis, or the management constraints and complexity that comes with all those different systems. So this is a transformative technology, this control and user plane separation, and the ability to leverage software really does unlock a lot of additional value, just even beyond the scaling. So for example, if you want to be able to evolve to the future and have a network that is 5G ready and has cloud native support, the software solution is what you're going to want. And if you want to have a footprint for multi-access edge compute or MEC, we have customers that are deploying servers where a portion of the server is used for the BNG function, and then they've reserved compute for additional applications to run there. And they can then, over time, without knowing exactly what the future is, scale either one, as needed. And then if they need to add additional compute, they can very easily, because it's like adding a line card, not adding a whole new system. And the other thing is, if you want to future-proof, to sort of manage risk and capture opportunities, and this kind of gets back to what features can you support? The other thing about software is you kind of can do anything with the packets. And so you can really future-proof your network in terms of what features might be required, and not get caught off guard where there's some new application that requires new capabilities from the network. And if you look at this specifically in terms of services and what is capable, in your traditional, sort of legacy BNG versus the software-defined BNG, the legacy platforms really have closed architectures that stifle innovation. They use proprietary ASICs, which are great at just forwarding packets, but really limits the features. You can only do what that ASIC is particularly capable for. And you also now have the hardware and the software tightly coupled. And so, if the hardware needs to be replaced because it's end of life, because not all components don't live forever. You now are replacing the software as well, and perhaps even using software that is fairly different because it's supporting maybe new ASICs or new architecture. And a lot of times these classical BNGs don't have a lot of open APIs, and there's been a lot of talk today about how important that is to really create that closed loop automation, and the software-defined networking needs to rely on these APIs. So with the software-defined BNG, it's completely software-based, so really any feature can be supported, and you don't have the limitation of any particular ASIC. Your hardware and software is completely disaggregated, so you can have a different lifecycle management for hardware versus software, and do hardware upgrades when you need to, do software upgrades when you need to, and not have them linked, and forcing you to do expensive upgrades of high margin hardware. And then, of course, the open APIs to integrate new services is an essential piece of this. And so it needs to be a system that's open and architected for innovation. And so any one of these types of services could be added and even integrated, into the BNG. So as you're processing packets in the BNG pipeline, as part of that same packet processing pipeline, you can support content filtering and do DPI. You can do SASE type security services. So all these things can be done, integrated in, so that you have a single pass architecture that looks at the packets once, decides what to do with them for all these different purposes, versus having a whole bunch of different nodes supporting all these different functions. And then finally, running on COTS servers really eliminates the lock-in on the hardware side as well as the software side, because it's completely disaggregated, the hardware and the software. You have flexible lifecycle management, like I mentioned. And of course, in this day and age, who would have thought supply chain diversity and agility would be so critical? And with an x86-based system, you have a very broad set of suppliers that you can leverage, and so you have a lot more diversity and agility in terms of keeping those lead times lower. So just to wrap it up, I think if you're trying to manage these market conditions, which are an increasingly unpredictable future, the rapid application innovation, device growth, the need for low latency, increased competition, wireless wireline convergence, you really need to think outside the box. You need to think about a system that is going to be really adaptable and agile, can scale, can support your distributed edge, but without enormous complexity in terms of deploying thousands of new separately managed nodes, and something that can support a lower total cost of ownership, add new services, and evolve. And that's one of the things we are really focused on delivering. And of course, this goes back to sort of our focus on having a heavily engineering-led organization that's really focused on innovating and driving value for our customers. If you want more details about how the performance scales and specific performance testing results, you can come to our website and download the white paper that explains this in more detail. So thank you very much. And with that, let me turn it back to Craig.